right? So 3.4 is all about the chain rule. What we're talking about is a derivative of a composition of functions. So y equals f composed of g of x, which I rather as f composed of g of x. They're both read the same way, but I think the second notation is easier. The second notation says I'm putting an entire function inside of another function, right? I'm putting an entire function inside of another function. So it's pretty easy to see that we're talking about here an outside function and an inside function. Now, I need a couple of things to be true. I need both functions to be continuous and differentiable, okay? But because you're going to see f primes and g primes in my answer, it should be obvious that they have to be differentiable. And if they're differentiable, they must be what? Continuous. If I'm going to find a slope, I have to be able to stand on a hill, right? If I'm going to find the slope of my skis, I have to be able to stand somewhere. So there can't be a hole in the graph, right? So I'm talking about this composition of functions, and we got this chain rule here. So if y equals f composed of g of x, then y prime is f prime of g of x times g prime of x. So I can see my inside function, right? I can see my inside function. I can see the outside function, right? And I can see the derivative of the outside and the derivative of the inside, yes? So, but this guy is still my inside function, right? This one is still my inside function. What I had inside originally is inside the outside derivative, right? So in words, I'll say the product of the derivative of the outside function evaluated at the inside function. There's the first part of my add, the product of, right? The product of this and the derivative of the inside function. The proof comes from that definition of the limit. And you're clearly going to see, you're going to find that definition again, right, by doing some creative factoring and then doing the limits. So you can feel free to go take a look at that if you're interested. I would say if you're a math major, definitely, but that's none of you. If you're a computer science major, probably. The rest of you, no. Okay? Now, I like to think, I have a loop for this as well, right? So I will take my outside function and the derivative and my inside function and its derivative, and I'll grab the letter C from it, right? So I see here, right, you can see the f prime composed of g, so that's inside, times g prime, right? So that's my little loop, and you can see I've got a letter C, chain rule, right? The way I really prefer to think of it is my outside function is a box, okay? And inside the box is a cat. Not that I'm a cat hater, but I'm going to push the box down a hill, okay? Now, all of a sudden, that box is changing its position, yes? So what do we have now? We have a derivative, right? How the box is changing, right? Maybe it's tumbling, depends on how cruel I am. Maybe it's sliding, right? But think about it. Now the box is changing its position. That's a derivative. What's still inside the box? The cat. So I'm keeping what was inside, even though the outside piece is changing. Couldn't the cat be freaking out inside? Couldn't the cat feel like sliding and start freaking out? And maybe now it's jumping all over the place. So now see what is happening to the box. So the box is changing with the cat in it, and the product of that change and how the cat is changing is giving me my overall derivative. So box changing with the cat in it, and the product of how the cat is changing, right? The cat is changing, sorry. Yeah, so this gives me what? Y prime equals box prime, still with the cat in it, right? Times cat prime. And you'll hear me say several times, keep the cat in the box, right? So whatever it is in the inside the first time, keep it on the inside. Let's do a couple of problems that are obvious, that don't need the chain rule, and do them with the chain rule and see that we get the same result, right? And then we'll move to something just with the chain rule, that we have to use the chain rule. And then some very complicated ones. Once I start adding a combination of product rule and chain rule, quotient rule and chain rule, they get very, very difficult, okay? So this is a big turning point in the class, right? Even though I've probably lost 1, 2, 3, 4, 5 students, I still could lose some more here, okay? So make sure you're practicing, make sure you're working on this, right? Do lots of problems. Your friends will forgive you, right? Because you got to take time from somewhere. Take it from sleep, take it from work. That's a hard one to do. Take it from friends. You can do the sleep and get rid of the sleep and the friends, and I think you'll be fine. Not all of them, not all the time, right? Now, one of my main thoughts that I want you to have is that you always do the chain rule, and you always have been doing the chain rule, okay? I just didn't let you know we've been doing the chain rule, right? So, for example, if y equals 1 square root of x, right? Y prime is 1 over 2 square roots of x times x prime, right? So I'm taking the inside function and getting the derivative of it. And what is the derivative in this case? 1. So 1 over 2 square roots of x times 1 is still my 1 over 2 square roots of x. I've been doing the chain rule the whole time. I think I asked you all to investigate what happens when you shift a function over, right? When you move a hill over and the skier is still on the hill, does the slope change? No, right? I think I had asked you to do something like y equals square root of x minus 3, right? So what do I get for y prime here? I get 1 over 2 square roots of x minus 3. Keep the cat in the box, right? Times x minus 3 prime. But what is the derivative of x minus 3? 1. So you see, if I do some kind of horizontal shift, my function doesn't change, right? The interior stays the same for the derivative, right? Whatever I started with, I end with, right? All right, let's do a derivative where I don't need the chain rule, but then I'll do it with the chain rule to show that I get the same result, okay? Say again? Yes, I can. Can I pause a second? Yes. So go ahead. Ian, what?
You did the derivative of the square root of x minus 3, that's 1 over 2 square root of x minus 3, and then you multiply by
The derivative of that inside function, yep.
which is
1.
Where is the inside function?
You tell me, what's the inside function here?
Oh, x.
Yeah, inside function here. Yep. Okay, so let me do one where I don't need the chain rule, but then I can use the chain rule, and we'll see what happens, right? So I want to do y equals sine 2x. Okay? Notice the inside function has a slope different than 1, right? The inside function has a slope of 2, yes? A derivative of 2, I should say, right? So I know I need the chain rule here, but I have an identity for this one, right? This is what? 2 sine x times cos x, yes? So I can do this with the product rule, right? First function is 2 sine x. Derivative of sine is cos, so 2 cos x. Remember, coefficients come for the ride for derivatives, for limits, right? Second function is cos x. Derivative is negative sine x. It's a product rule. I can take my product in any order, right? Any diagonal product plus the other diagonal product. So I'm going to take the second one first. I'm going to take this one first just because I want to. So y prime is 2 cos squared x minus 2 sine squared x. Agreed? Agreed? I can factor out the 2, and then I should see an identity. So y prime is 2 times cos of 2x. Yes, we're okay? Same problem with my chain rule now. Don't let me go too fast. We ready? Almost. Morning. Okay, we're ready? Nice. Looking at my function, my original function, right? I can clearly see the outside function, right? It's sine, yes? So I want to think of that in general. I want to say, okay, The outside function is sine of x. What's the derivative of that? Cos of x, right? And the inside function is 2x, and the derivative of that is 2. And Daniel, I recorded, so.
What is the derivative of sine x equals to?
Oh, because Robert was thinking about the inside function already. Thank you. Right? Sine of x derivative, sine of x is cos of x, right? Now I'm going to take the derivative of the outside, right? And evaluate at the inside. And then multiply by 2. So I get y prime is 2 times the cos of, what was the cat? What was originally in the box? 2x. There it is, same answer. And you can see why we came up with this chain rule. We started to notice patterns in our derivatives and kind of discovered, well, wait, doesn't that look like the derivative of the outside times the derivative of the inside, right? And so that's what we're good at, humans, recognizing patterns. And then if we're good mathematicians, we prove them. Instead of this loop, I like just thinking of the outside function. So derivative of the outside is cosine. Keep the cat in the box, then times the derivative of the inside function, right? We okay? Another one? Let's do one that we have to do with the chain rule, okay? Question, Yvonne?
Yeah, why would we do all of that?
I'm sorry, I can't. You got to speak a little clearer for me, a little louder.
Like all the below parts, like all of this, you could have just plug in the C.
I'm trying to at least convince you that I get the same answers from the process, because I'm not going to prove it to you, okay? So I'm just trying to convince you that, hey, it seems like it works, right? All right, let's do one where we have to do it with the chain rule, right? So let's say, sure, back? Yep. The right-hand side? Right-hand side? Yep. Yes. Nice. So f of x, is square root of 1 minus 3x. The outside function is a square root, right? So I know I need 1 over 2 square roots, but I want to keep the cat in the box. I want whatever was inside originally, I want to keep it in there, right? So inside piece is 1 minus 3x, and then I need times the derivative of the inside piece. Outside function derivative, keep what's inside, then multiply that by the derivative of the inside. So I get a final answer of f prime as negative 3 over 2 square roots of 1 minus 3x. How are we doing? Let's do another one that we can do without the chain rule, and then we'll do it with the chain rule. All right? And then maybe why don't we get a tangent line on this one too, okay? Why? Because I'm going to give you one with a tangent line on quiz Thursday, so you can all save face right on your trig. So let's do y equals sine squared of x. So once I get my derivative, then I'll decide where I want to do my tangent line, right? So let's do this with the product rule. Do you see it as a product rule? Yeah. So as a product rule, I really see y as sine of x times sine of x, right? So my first function is sine of x. Derivative is cos of x. Hopefully you're not copying here, but you're having the same voice that you hear me saying, right? Second function is sine of x. Derivative is cos of x. So what do I get for y prime? I get sine x cos of x plus another sine x cos of x, which is two of them, 2 sine x cos of x, which is sine 2x. Hey, nice. This particular piece is on every one of my midterms. This derivative is on every one of my midterms. Nice. Let's do now the chain rule, right? Do we always do the product rule? No. Do we always do the chain rule? Yes. Right? So we're going to do the chain rule here. And I have y equals sine squared of x. It's easy to think of the chain rule of inside and outside if I rewrite as the sine of x function all squared, right? So you can see what this outer function is, yes? The outer function is the x squared function, power rule, right? So when I take the derivative of something squared, I get 2 times that something. Agreed? And I want to keep the cat in the box. So y prime is 2 times the sine of x times the derivative of the inside, which is the derivative of sine of x, right? And that is cos of x. So 2 times sine of x times cos of x, and there it is, sine 2x. Do you want to see that as a loop? Anybody want to see that as a loop? Yes? So my loop, I'm thinking the outside function is x squared, right? I see something squared, so just call it the general something squared, which is x squared. And what's my derivative of x squared? 2x, right? And I've got the inside function as sine of x, and the derivative of that is cos of x. So I want to take this function, evaluate at sine. Sorry, I'll do it like this. I get a fancier C here. So I'm putting that sine x into the x of f prime, right? So y prime is 2 times, right? That's sine of x times the cos of x, g prime. I'm stretching it a little bit on my loop. I'm trying to make it look like a C, but I'm trying to wrap it in the loop of the C so that you can see that piece that inside piece, that function g, goes inside, right? I plug it in as a composition, right? Okay? Let's try a little bit of tougher one, and then we'll go to the one that's on every midterm I ever give, right? Every midterm has one just like the, I don't like to give the easy problems. I like to give you the difficult problems. But they're all on my old exams. And I'm pretty lazy. I'm going to take an old exam, or maybe 2 or 3 of them, and take problems from them, and then maybe change them. I might change the sign to a cosine. I might change an x squared to a negative x squared, right? So the idea is that you practice the old exams, right? So let's look at one, okay? Let's do a second derivative of y equals e to the minus x squared. Notice the inside function is complicated, isn't it? Right? Right, the simple version of this function would be e to the x, right? Yeah? So this inside function is quite complicated compared to x, right? Derivative of x is 1. Derivative of minus x squared is negative 2x, right? Now all of a sudden I have a variable derivative, right? So, but see if we can get y prime right away. I need to keep, if it's an e to the x function, my derivative stays the same and the cat stays in the box, right? So I still get e to the minus x squared, but then I want to multiply that by the derivative of the inside, right? Which is minus x squared prime. Notice here, I'm trying to take my time here by putting a placeholder in. I can get the derivative of the outside quick and keep what's inside, and then put a placeholder down of, I have to take the derivative of the inside, right? And so what do I get as this, for this answer of y prime? I get negative 2x e to the minus x squared. Yes. So the loop would be e to the x. Derivative of that is e to the x. The original inside is minus x squared. Derivative is minus 2x. I'm going to take the e to the x, right? Wrap it in that negative x squared, right? And then multiply by the g prime. So notice the g prime is here, right? And then this is f prime evaluated at minus x squared. That's a g. Right? Do you see that this piece is going into here? Keep the cat in the box. I personally am, I like to think of innies and outies, or even Mercedes-Benz. It's a joke. Outies, inside functions, outside functions. I prefer to think that way, but I'm trying to give you the option of the loop if it clears anything up for you. I want a second derivative, right? You with me? But I can see here that y prime is negative 2x times f, isn't it? Or times y, better yet, y. So I'm going to do a product rule here, right? my first function is negative 2x. The derivative is negative 2. The second function is y, which I know is on my page, and I know that derivative as well. That's y prime, also on my page. This little shortcut I'm doing here will save sometimes some paper, right? And in chapter 4, it will save your sanity when we have a 6-page problem to do. Oh, this is y double prime, I'm sorry. That's y prime. No, that's y prime. Now I get y double prime, right? So I get negative 2x times y prime minus 2 times y. Say again? Yeah? Yep. Okay, well, I know y and I know y prime, right? I get negative 2x times y prime, which was negative 2x e to the minus x squared, minus 2 times e to the minus x squared. And if you can remember my goal, right? My goal was always to factor. Don't want to distribute here, I want to factor. So I clearly can take out a 2. I can take out an e to the minus x squared from the first term, right? From the green term, what's left over? Yep, 2x squared. And from the second term, what's left over? Negative 1. Now I want to talk about, how are we doing? We okay? I want to talk about critical values here. I think I've mentioned it several times. It's chapter 4, but I often ask you for them on the midterm. I'll say, find me the derivative and find me the critical values of the derivative. Or find me the second derivative and find me the critical values of the second derivative. So critical values are when my numerator is 0 or my denominator is 0. So the critical values of the derivative are what? When does this thing equal 0? When x is 0, that's the only time, right? In fact, it would be fair of me to give you the graph of this first of all, right? So this is the graph, it's the bell curve. This is y equals e to the minus x squared. And we got our critical values of the first derivative, we got x is 0. So at x equals 0, there is a horizontal tangent line. Obvious, right? At the top of the hill, yeah? What are the critical values of the second derivative? Look at the second derivative here. It's only 0 when this is 0, right? Yep. Y double prime equals 0 implies 2x squared minus 1 equals 0. That's what? X squared equals 1/2. That's x equals plus or minus rad 2 over 2. So about 1.7 and negative 1.7. Wait, square root of 2 is 1.4, sorry. About 1.4. You can see I'm changing my steering. Imagine I'm looking down on the road from a helicopter. I'm looking down on the road from the helicopter. So I'm not driving up a hill, okay? I'm driving on a road that turns like that, right? And you can see I'm turning my steering wheel to the left. I hit that first black dot. I'm turning back to the right. I hit that next black dot. I'm turning back to the left again. Critical values of the first derivative give me horizontal or vertical tangent lines. Critical values of the second derivative give me inflection points. I will when I teach that. I want to, but that's chapter 4, right? So I don't have to, we don't have to write that down yet, but what we want to know is what's a critical value, when the numerator is 0 or the denominator is 0. That's what we need now. Yes?
Can you go up for like 1 second? Only a tiny bit. Yeah, like right there.
Yeah.
Okay, cool. I'm gonna-
So chapter 3 is all about derivatives. Chapter 4 is about applications of derivatives. What do derivatives tell me? Right? And then chapter 5 is undoing derivatives. Nice. Let's go to let's take a 7-minute break, and then we'll do a couple of difficult ones. Okay. Yeah. Here's my chapter 3 test from fall 2019. I think I have about 3 of them. And you can see the first problem is a chain rule problem. The second problem is a chain rule problem. I'm looking at the inside-outside piece of it. What about the third problem? Chain rule? Just quotient rule, right? We don't need the chain rule there. Fifth problem. This one is this is an inverse trig, but it's a chain rule. What's the inside function? X squared, right? The next function is an exponential function. We didn't do that yet. That's 3.7. Number 7 is an inverse trig. That's 3.6, but that's also a chain rule, right? Inside function is arcsine of x over 2. Find the critical values. Look at that function. Doesn't that look familiar? Looks almost like the exact one we just did, right? Second derivative, critical functions of the second derivative, right? 9 is a chain rule and something called implicit. Okay, so that's 3.5. We're doing 3.4 right now, right? And the last one is implicit too. So, nice. Here we go. This is from fall 2019, chapter 3, test number 2, right? Fall 2019. Remember the good times? Chapter 3, test number 2. So I want a function. I got a function here, as soon as I could find it. Yeah, f of x equals x squared minus x to the third times 2x minus 1 to the second. You'll see the calculus is pretty damn easy. The algebra, hideous. Okay? So some of you need to be practicing your trig. Some of you need to be practicing your factoring, right? Where else have we had trouble? I think that's about it. Factoring and trig is the biggest issues I see right now, right? All right, first function. So this is a product rule, right? How do I know it's a product rule? I'm multiplying 2 functions together. How do I know it's a chain rule? I always do the chain rule, forever, right? I'm always doing the chain rule for the rest of my life, right? I'm thinking about what I had for breakfast, right? And how much energy it's giving me. So I'm moving with my breakfast in my stomach, and my body is processing the food. That's the inside prime, right? And the product of those things tells me how I'm changing. Outside, moving with this breakfast inside, and then I'm getting energy from how that breakfast is being processed by my body, right? Even though I'm diabetic, it's still doing something. Not doing great stuff, but. So first function is x squared minus x quantity cubed. What's the exterior function? It's an x cubed, right? So when I take the derivative of an x cubed function, I get 3 times x squared, right? So f prime is 3 times x squared minus x all to the second power. Notice I kept the cat in the box. But now I need the inside prime. What's the inside prime? 2x minus 1. Good. How are we doing there? Only 1? Student okay? 2, nice. 3, I can see you. The green? Yep, that's the derivative of the inside, right? So I could rewrite this as times x squared minus x prime, right? I'm going to take the inside piece and take the derivative of it. Good. Second function is 2x minus 1 quantity squared. So I see my exterior function, my outside function is an x squared function. I know my derivative is 2 times x, right? Or 2 times the inside. So g prime is 2 times 2x minus 1 times, again, what's the derivative of the inside? A 2. Right? The derivative of 2x minus 1 is 2. Calculus is done. The calculus is easy. The algebra is not. But it should be a review. Okay? So you know how to do it. At least your teachers in the past have said, all right, you're ready to move on. Okay? Now, I didn't do anything in high school and they passed me, right? But hopefully it's different in college, right? So we can't shortcut it. We can't lie to ourselves. We got to be able to do everything. I'm going to do this product rule, right? And I'm going to put things in order as I go, okay? So if you see, I'm going to take this product first. But I'm going to pick things in a specific order so that I keep coefficients and matching factors kind of lined up, okay? So for y prime, I'm going to get 4 times x squared minus x quantity cubed times a 2x minus 1. Everybody see where I'm getting that from? Got my coefficients, and then I got my factors, right? Plus, now I'm doing this one, right? So plus 3 times, what? 2 times 2. Plus 3 times, it looks like I need my, help me, x squared minus x to the second, right? X squared minus x to the second, yes? And then I have 2x minus 1 to what power? Third. Make sure you see that. Everybody okay here? I can factor out an x squared minus x to the second, Do you see that? I can factor out an x squared minus x to the second power and a 2x minus 1 to the first power. What do I have left in the first term? I have 4 times x squared minus x squared plus 3 times 2x minus 1. Oh, wait, I can take out to the second power, sorry, right? I'm sorry, let me go back. Notice I have a second power here and a third power here, so I can take out a second power, right? Sorry about that. And so now, right, this is, yes, say again? What? Yes, thank you. Now, I've got a little cheater there if you need to see it, okay? If you need to see it, I can show you a quick cheat there, because I think that part right there is tough sometimes. So the cheat is to kind of think of this as 4 times x squared minus x squared times an x squared minus x and a 2x minus 1 plus 3 times x squared minus x squared times a 2x minus 1 times a 2x minus 1 squared. And now I can really see the matches, right? I split it so that I can instantly see what's matching and what's left over, right? Do you see what I'm saying? Anybody? So I can split it. Before I go to factor it, I can break those shared factors down to where they match exactly, so I don't have to think about the exponents, okay? All right, I gotta keep going. This piece is not factored. The only way to factor it is to distribute and get common, group common terms, right? So look for that. If you end up with a sum or difference, and I say factor everything, you got to see if that thing factors, right? So you got to distribute that out. So what do we get? X squared minus, oops, oh, I did something else bad, sorry. X squared minus X there, right? You gotta catch me on these. What do I get? I get a 4x squared minus 4x plus 3 times 4x squared minus 4x plus 1. Right, so I'm distributing and I'm double distributing, right? Foiling there. So we've got x squared minus x quantity squared, a 2x minus 1, a 4x squared minus 4x plus 12x squared minus 12x plus 3.
So how do you decide that that part needed to be expanded but not the first?
So it's not factorable, and it's a sum, right? Nothing shared with the 4 and the 3, right? So the 4 and the 3 they don't have a common factor, and this piece and this piece don't have a common factor. So when I get there, and it's a sum, I've got to try and distribute things out. And if I do enough problems, like the ones in the book and the ones I assigned in WebAssign and the ones in my Chapter 2, Chapter 3 test and midterm exams, I should be a master at this before this quiz. This particular quiz is in 2 weeks, right? Not this Thursday coming up, right? This Thursday coming up is, continuity, L'Hopital's one more save face with the trig tangent, right? The following week after that will be product rule, quotient rule, maybe chain rule. We'll see how you're doing, right? We'll see how you're doing. I can simplify this. I get 16x squared minus 16x plus 3. And I have to decide if this is factorable, right? So I got to do a little side work here. 16 times 3 is 48. Negative 4 times negative 12 is 48. And negative 4 plus negative 12 is negative 16. So I got it, right? So I'm going to keep working on the side here. 16x squared minus 16x plus 3. And I'm going to split the middle term, right? So I get 16x squared minus 4x minus 12x plus 3. I got a common factor of 4x and a common factor of negative 3. So there it is. I've got y prime is x squared minus x quantity squared. 2x minus 1, that quantity of 2x and minus 1. Then I've got a factor of 4x minus 1 and a factor of 4x minus 3 for my side work. Still not done. Do you see anything else common? It's right in here. You see anything common there? If I could think of just one of those x squared minus x's, there's a common factor of x. But since I'm squaring it, there's a common factor of x squared. So here's my final answer. X squared times x minus 1 quantity squared times quantity of 2x minus 1 times 4x minus 1 times 4x minus 3. Done. Ouch, right? What are the critical values here? Nice, 0. 1. Yeah, 1/2. Yep. 1/4. And 3/4. Yep. Right, I'm asking where each of those factors are 0, right? Where the numerator is 0, where the denominator is 0. There's no denominator, right? You ready? Another one? Can you handle it? Can you hear me?
Yes.
Okay. I'm hoping by the end of spring break we're back in here without masks. It's my prediction. All right, let's take a look at a problem from section 3.4, okay? When you're doing homework for this class, make sure you're getting the homework from the textbook, not from WebAssign, okay? I have the original textbook link in the first announcement, right? First announcement, so it's what, it's, oh no, that wasn't it. Where the heck is it? Oh, here it is. No, there it is. Stewart Calc book, right? I like the way it opens here. You can see that, you can see every page of the book. So there's that front blue page that should almost all be on your formula sheet unless you know them, right? And then I think we're almost through page 5 of the back reference pages. So these are the back reference pages, and we should be up to, there's a bunch of Calc 2 stuff. Calc 2, Calc 1, Calc 1, Calc 1 and Calc 2. We start chapter 5 in Calc 1, we finish it in Calc 2, and that's all these integrals. And then, oh, here are, wait, where are our derivatives? No, sorry, I passed it. Yeah, general derivatives. So yeah, page 5, right? We're about to do inverse trig functions. We're not doing hyperbolic or inverse hyperbolic functions. You'll do some of those in DiffEqs from the engineers. Some of you, the engineers will do hyperbolic functions. The hyperbolic function is pretty cool. If you imagine the Golden Gate Bridge or Brooklyn Bridge and they're hanging a wire down, it looks like a parabola, but it's actually a hyperbolic function. It's not an x-squared function. All right, so anyway, I want to go to chapter 3, 3.4, and let's pick a problem there to do. What do you think, 23 or 24? Let's do 23. So some quantity cubed, right? And then the inside is x squared plus 1 over x squared minus 1. Yeah? Anybody need another minute? I'm going to write it down so you can finish copying off of mine if you're still writing. So I've got y equals quantity cubed, and I had x squared plus 1 over x squared minus 1. When I start getting this product rule, quotient rule in between, I'll often use placeholders, okay? So I already know that y prime is 3 times that inside squared times the inside prime, right? You got me? So I'm trying, it's complicated, right? I know the derivative of the inside is complicated, so I'm trying to write my derivative down with a placeholder of saying, reminding me, I still have to do that quotient rule part, right? So the quotient rule part, I'm going to work on with my loop. Upstairs function is x squared plus 1, derivative 2x, right? Yes? Downstairs function, x squared minus 1, derivative, oops, downstairs function, x squared minus 1 derivative 2x, all divided by x squared minus 1 quantity squared, right? All divided by the downstairs function squared. So this is my side work, right? This is my Q loop, right? So what do I get for star here, right? I'm doing my derivative of my quotient loop here, right? I get 2x times x squared minus 1 minus 2x times x squared plus 1 all over x squared minus 1 quantity squared. Just doing a little side work. I'm not going back into my derivative yet. It's still too messy, right? So, but what am I going to do here every time? Factor. I want to factor. Don't want to distribute. I want to factor out the 2x upstairs. And I get x squared minus 1 minus x squared minus 1. So it looks like I get negative 4x over x squared minus 1 quantity squared. There is finally my, right, my little quotient rule there. Now I'm ready to go back to my original derivative. Y prime is 3 times x squared plus 1 over x squared minus 1, that all to the second power, times a negative 4x times an x squared minus 1 to the second power. Nice. So I'm just picking pieces from the numerator here, right? Minus 12x times x squared plus 1 all squared over x squared minus 1 all to the fourth. I want my function, my derivative as a single fraction, completely factored. What's nice about these is you don't need, so I gave you odd solutions, but these are just derivatives, right? So you can even do some even problems from the book and check, right, on Symbolab, like for example, number 20, right? Look familiar? 20 is like the one I just did before this problem, right? Yeah. It's kind of fun when they get nested, like thinking about the box with a cat in it, and the cat has got a mouse that it just ate, and the mouse just ate some cheese, kind of thinking, right? So the mouse is changing as the cheese is being digested. The cat is changing as the mouse is being digested. The box is changing as the cat is changing, right? So if you think about that, they can get crazy. I tend to not do problems like that, but it's fun to look at one. So like, for example, say again? Yep. So like number 32 is kind of fun. Sine of x. Let's see how we do with it, okay? Again, I don't typically do these problems. So y equals sine of x. So for the original outside function, it's just a sine function. What's the cat though? Sine of x, right? So what do I get for y prime? Think about it. What's the derivative of sine? Cosine, but I'm going to keep the red cat in the box. Sine of x times the derivative of the inside, right? So that's sine of x all prime, right? I'm putting a placeholder there. So, nope. So remember, I'm doing the derivative of the outside, which is a cosine.
Yeah, and the derivative of
The inside is sine of, right, in red, sine of. And then the derivative of the inside. I keep the cat in the box and then get the derivative of what was inside, right? So now we're looking at the blue-red, right? We're looking at that. So far for y prime, I have the original outside, the original inside, and now I'm ready to do my derivative of the green-red, yes? What's the outside function there? Sine, so the derivative is cosine, and keep the sine inside, and then take the derivative of the inside. Yep, so from line 1, right, in line 1, I've got an outside function of sine, and an inside function of sine of x. The derivative of the outside is cosine, so there's my cosine, right? And there's my inside again, and then the inside derivative, which I haven't done yet. I put a placeholder there. So I still have this part here in my answer, and now I'm doing the derivative of the inside. Derivative of sine is cosine, evaluated at the inside, times the derivative of the inside, which I haven't done yet. What is the derivative of sine of x? Cos of x. So I'm finally there. Cos of the sine of x times the cos of the sine of x times the cos of x. So they're kind of fun when they're nested, but I don't ask. You won't see anything. You might see one on my earliest chapter 3 test, but I stopped doing them. Not that important. There's never any factoring with stuff like this, so it's too easy is what happens. These are too easy. Because it's not the calculus that's tough, it's the factoring that's tough. Right? Go ahead. Diego, what's up? One more time? Yes. How do I know? Well, when I'm working on things, I'm going to look in the book, right? And see if it's the right answer. Or on Symbolab, right? And then if you think about it, I have an inside that has an inside, right? I have to make sure I keep taking derivatives of insides as they come, right? So how many times am I going to take a derivative if I have an inside of an inside, right? I have to take the derivative of the insides at least twice, right? And if I look at this last piece, what's the derivative of the inside of that? 1. So do I need to go further? No. I don't know if if I could do any more to you today without overloading you. So have a good day. See you Thursday.